Good evening, everyone. Welcome to the last and 12th session of 12th interactive session of Structural Analysis 1 course. So we have had 11 weekly sessions until now, and each of them dealt with various methods, such as the various methods for computing the deflections, various methods for analyzing the statically indeterminate structures, and we classified them as force method and displacement methods of analysis. And finally, we ended with a displacement method of analysis, which is the direct displacement. So that by last week we have completed all the contents of the course, and we have also solved the previous year assignment problems. So today, since you don't have to submit any assignment this week, you'll directly have the end exam next week. Today, I will be brushing through all the concepts covered in the course and also solve some problems, some challenging problems from all the topics, so that it would help you revise for your examination. So the recording has started. Let me share my screen. So this presentation summarizes all the methods that we have seen in the course. So method of starting from the methods available for analyzing statically determinate structures like trusses and beams and frames, till the methods for analyzing statically indeterminate structures such as the three-moment theorem, displacement-based methods, and the relevant equations have also been inserted. So I will upload the presentation to the folder as usual, so that it may be helpful for your preparations for the final exam. Let me go to the presentation mode and get started with today's content. Also, another thing, in case you have any doubt, so this session is meant for you. Whenever you have any doubt with any of the methods, you can stop me right there and get them clarified, because yeah, we have looked at all methods. There is no new concept to be covered, so you can ask any doubt and I'll get it clarified. And if you want some extra problems to be solved in this session also, please let me know. I have access to many problems. I'll take one out of, I'll take one for each method and I can solve it. So if you request. Let me get started with the presentation. So welcome everyone to the 12th problem solving session for structural analysis 1 course. This will be a summary of all the methods that we have studied in this course until now. Let's quickly get started with the basic concepts involved in structural analysis. So we know that it is a systematic procedure to determine all the internal forces, stresses, strains, and displacement at various points in a structure, when we are given some specified loading and support conditions. So this is what we have been doing throughout the course. And why we are doing it? It's because we are interested in finding what is the forces and moments and the actions that come onto a particular member. So we are interested in carrying out design of structures, but in order to carry out design, we need. So design is basically if we have. So we want the actions coming onto a member to be less than or equal to the resistance of the material. So structural analysis is one method by which we can find out what is the action that is coming onto a member. So structure is a very complex system, and we find out what is the load acting upon each of the small members, so that we can design each of the elements for a specified, so that we can choose the member dimensions and the material such that it safely transfers the applied load. That is the idea. And we also know that structural analysis is, the analysis involves three basic principles. One of them is the equilibrium of forces and moments. The next one is the force displacement relations for various types of members. And the last one is compatibility of displacements in the structure. And throughout the course, we limited ourselves to linear elasticity, where the material response is essentially linear elastic. So elastic means the material has no memory. The instantaneous force is depending only on the instantaneous displacements applied. Not only that, if it is linear, it means the relationship between the two is proportional. And it also, and we're also limiting to small deformation. That is, we established equilibrium of all the forces in the undeformed configuration. We didn't consider the deformed configuration. So here are the methods of analysis we used for statically determinate structures. So one part of it was to determine the internal forces in various members. So for trusses, for truss structures, we saw two methods. One is the method of joints, where we establish equilibrium at every joint and we proceed onwards. And the other method was the method of sections, where we make an imaginary cut through the structure at a point where we need to determine the member forces. And for beams, there's only one method. We didn't go through the method of joints. We used the method of sections to determine the internal axial force, internal bending moment, and the shear force. The other part of the course in statically determinate structures was finding deflections in various structures. One of them in beams is the double integration method, where so one is the double integration method. So we use the moment curvature relation, and curvature we approximated as the double derivative of the displacement deflection profile. And then we integrated twice with appropriate boundary conditions and continuity conditions to determine the deformed shape or the elastic curve of the beam. And the other method we looked at was the moment area theorems. So we had a pair of theorems called the moment area theorems, which related the bending moment diagram to the various displacement and rotation fields. And then we looked at conjugate beam method and the unit load method based on the principle of virtual work for both beams and trusses. In addition, we also looked at various tricks such as the principle of superposition, virtual work, and I also talked about Maxwell's reciprocal theorem based on the principle of virtual work. And we also looked at influence line diagrams. So what are influence line diagrams? Influence line diagrams are basically some diagrams that help us identify the maximum load or maximum reaction or the maximum internal force that is attained at a given point due to a load that is moving across the length of the beam. So the influence line diagrams do not, by themselves, do not contain any new method of analysis, but given a method of analysis, constructing the influence line diagram is very helpful in design. So that is the principle. And then we looked at statically indeterminate structures. So we classified the methods of analysis of statically indeterminate structures into two. Force methods of analysis where the primary unknowns, right? So we looked at the force methods of analysis where the primary unknowns were the redundant forces in statically indeterminate structures. And what else? If the degree of static indeterminacy was ns, we got an ns cross ns system of simultaneous linear equations. And in the displacement methods of analysis, the primary unknowns were the unconstrained degrees of freedom or unconstrained displacements. The unconstrained degrees of freedoms or the displacements and rotations. They were the primary unknowns in the displacement methods of analysis. And we got an nk cross nk system of linear equations. And force methods of analysis obtained the unknown redundant forces by enforcing compatibility. On the other hand, the displacement methods of analysis obtained the unknown forces unknown displacements by enforcing equilibrium. So that was the key ideas in both the methods. Beyond that, so in the force methods of analysis, we looked at uh, the Klepperon's theorem of three moments. We looked at the method of consistent deformations. So Klepperon's theorem of three moments related the moments in two spans. So we took two spans of a continuous beam at a time, and then we identified what are the moments acting at the joints in the span, and then we got a relationship between them using the compatibility of the rotation at joint at the middle joint. Then we also looked at the method of consistent deformations, where we identified the redundant forces, isolated them, constructed a primary structure which is statically determinate and stable, and constructed the entire structure by a superposition of the action of the external loading, the action of the redundant forces, and finally enforced compatibility at the points of action of these forces. Then we looked at the displacement methods of analysis for beams and trusses. So for beams, we looked at the slope deflection equations, moment distribution method for both beams and frames, and also the direct stiffness methods towards the end of the course. For trusses, we don't have any force deflection, slope deflection, or the moment distribution method, so we looked at the direct stiffness method. So let us quickly get into the basic ideas. So what are the equations of equilibrium that we looked at? So we mostly confined ourselves to planar structures, and the equations of equilibrium are the summation of all forces in the x direction is 0, summation of all forces in the y direction is 0, and summation of the moments above the z-axis is equal to 0. And then not only that, we also looked at the concepts of static determinacy and stability. So when do we say a structure is statically determinate? We say that when the number of equilibrium equations is equal to the number of equilibrium equations when it is equal to the number of unknown forces. Then the equilibrium equations are alone enough to find all the internal forces and the support reactions. So such structures, we call them as statically determinate structures. And if this condition is not satisfied, that is, if there are more unknowns than the equations, then we call them statically indeterminate structures. We also looked at what is kinematic indeterminacy. So this the degree of static indeterminacy. So if it is a statically indeterminate structure, we define the degree of static indeterminacy as the number of unknowns minus the number of equilibrium equations. And we also define the degree of kinematic indeterminacy as the number of unconstrained displacement degrees of freedom. So displacement is a generalized terminology. We can also include displacement, and we should also include rotations. So it is the number of unconstrained degrees of freedom in the structure. So this is the kinematic indeterminacy, which plays a major role in displacement methods of analysis. And this is the static indeterminacy, which has a major role in force methods of analysis. We also looked at the concepts of stability. So in stability, when do we say a structure is stable? So a structure is said to be stable if under small perturbations but arbitrary. Under small arbitrary perturbations, the structure shouldn't accelerate. It shouldn't form a mechanism. It should still be able to safely transfer the applied external loadings. So this is the concept of stability. So we are only dealing with stable structures in our course, but you may have exam questions where you may have to identify if a structure is stable or unstable. In those cases, what do? You just consider, suppose you are given some structure, something like this. You apply a small perturbing load and physically you imagine how the structure is about to deform. So examining the way in which the structure is likely to deform, you can establish its stability. We also looked at various methods to identify zero force members in trusses. So we particularly looked at two conditions. So these are just for tricks in an examination. So if you have two non-collinear members, at a joint without any load. Then both of them are zero force members. And not only that, if you have three members, out of which two are collinear, and there is no force acting on this, then the non-collinear member is a zero force member. So either you have two non-collinear members at a joint without any load, or three members with two of them collinear. In that case, the non-collinear one has zero force in the thing. Then we looked at the principle of superposition. So principle of superposition holds only in linear elasticity. It does not hold in either non-elastic members, non-elastic structures, or non-linear elastic structures, or non-linear inelastic structures. So it holds only in linear elasticity. And what does it say? Suppose you have a certain structure, right? You can, or not even a structure, you can have a certain body as well, subjected to some support conditions and some loading. The action of two different loadings on the body can be obtained as a superposition of each of the actions taken one at a time. So you first consider this load, find all the internal displacements, forces, reactions, and stresses, and add it with all the internal forces, reactions, and stresses and displacements obtained by applying F2. So if you have a combination of loading F1 and F2, you first consider F1, find all the solution, and then consider F2, find all the solution, then add both. So that is the principle of superposition, which we'll be using very often in our in this revision of the course. Then we looked at the method of joints. So a very basic method that you're familiar from engineering mechanics. So the key principle in this is if a truss is in equilibrium, then each of its joints must also be in equilibrium. So the procedure is first find the support reactions. So if the structure is statically determinate, how do you find the support reactions? We enforce the equations of equilibrium. Then you start with a joint with at most two unknown forces. So in order to find the support reactions, you need the three equations of equilibrium because it is an extended body. Sigma fx equal to 0, sigma fy equal to 0, and the summation of all moments is equal to 0. Once you have determined the support reactions, you start with an external joint. So if you have a truss, you start with an external joint where you have at most two unknown forces. So this is an unknown force, the member force in this, and this is a member force. This member force is unknown. You know that all the truss members are two force members. So at a joint, we can always take the magnitude of the force along each member as unknown and direct the force along the orientation of the members connecting to that joint. So you can have at most two unknown forces. Why? Because the joint is a single point and a point has only two equations of equilibrium, which are sigma fx equal to 0 and sigma fy equal to 0. It doesn't have any moment equation of equilibrium because it doesn't have any, it's not, all joints are pin connected, so there's no moment acting on any of the joints. All forces are assumed to be collinear at a joint, concurrent at a joint. So you have only two equations of equilibrium. Apply these two. So since we have only two equations of equilibrium, you start with a joint that has only two unknowns. If you have more than two unknowns, then you cannot solve the problem. Once you have solved for the unknown member forces, denote the member force in that member, and then move on to the joint where this member is framing into, and repeat this until all the member forces have been determined. And also apply an appropriate sign convention. If you start assuming that all members are under compression and you get a positive sign for a given member, then it means the assumed direction, which is tension, is a correct answer. So you assume all members are in tension. That's a good assumption. So if you assume all members are in tension, then if you get a positive sign, it means the member is actually under tension. And if you have a negative sign, then it means the member is actually under compression. So moving on to the next method of analysis, which is the method of sections. So you see that if you have to determine the member force in some particular member, suppose you have a complex truss. And you're required to find only the member in only the force in this member. Say, let me call the member AB. We see that it's a tremendous task to start with and suppose there are some loads acting on this truss. And you can easily see that if it's a tremendous task to determine all the member forces and then come to this joint AB. Instead, what you can do is take an imaginary section. So you take an imaginary section through that member and cut the structure into two parts. The two parts don't have to be equal. So cut the structure into two parts. And the key principle is that if a truss is in equilibrium, then every part of it must also be in equilibrium. Once you have cut the truss, you consider one of the parts. So since the truss is in equilibrium, each of its parts is also under equilibrium. So consider suppose the left part, and we know that trusses are all two force members. So denote the forces acting along the member. So we know the direction of these forces, only the magnitude of the forces is unknown. And if you have already determined the reactions, so the steps are first find the support reactions, make an imaginary cut through the members where you need to determine the unknown forces, then apply equations of equilibrium to any one of the parts, one of the two parts. And once you have applied, so why do you need to cut through at most three members? Because this is an extended body. We have three equations of equilibrium. So since we have only three equations of equilibrium, if you make a cut through more number of members, say if you make a cut like this, you will not be able to determine the member forces with three equations of equilibrium for each part. So you need to make sure that you cut only three members at a time. Then take moments about a point so that is fine. Then while enforcing the equations of equilibrium, you have two tricks. And one of them is if you have two members that are two forces that are concurrent at this point, take the moment of all the forces about this point, so that you don't need to solve a system of 3x3 equations. Since these two forces act through this point, they will have no moment, and this will be the only unknown that needs to be determined at one time. Once you have determined that, then take equilibrium of forces perpendicular to the two parallel forces. So in this structure, you have two parallel forces. So this force is parallel to this force. Now, if you take the equations of equilibrium in this direction, only this force will contribute, which means you have one equation and one unknown. You can get it directly. So although you have three equations of equilibrium, you can solve for all of them by solve for them one at a time by using this trick. Then as in the last case, if you have assumed everything is in tension, then if you get a positive sign, then it means that the members are actually under tension. Now let's go to the method of sections for beams and frames. So we know that unlike a truss, and unlike truss members, which are two force members, beams and frames are subjected to multiple internal forces. So they're also called stress resultants. So if we have if you cut a beam at a section, there are lots of forces acting through the section. There are normal forces and there are tangential forces. If you sum all the small tangential forces acting through the section, then what you get is called the shear force. If you sum all the forces acting normal to the section, then what you get is the axial force. If you take the centroid of the cross section and take moment of all the forces acting through the section, and there you get the bending moment. So these are the resultant of the stresses acting through the cross section. So they are known as stress resultants. But note that here, if you make one single cut in a beam, you are exposing three unknown forces. One is the axial force, shear force, and the bending moment. So here the workflow will be first find the support reactions as usual. Then you set up a local coordinate system for every segment, right? So here it is not just enough to identify the internal force, because the internal force itself varies through the length of the beam and a frame member, because you have transverse loading. So a truss is always loaded at its joints, but a beam member like this or a frame member, a frame member like this is subjected to transverse loadings along its length. So this transverse loading results in a continuous variation of all the internal forces over its length. Hence, you cannot determine something called as the force in a member. You need to determine the force function, the bending moment function, shear force function, and the axial force function along each of the frame members. So in order to determine that, you set up a local coordinate system for each member. So we call this x1, call this x2, and you take this as x3. X3, y3, x1, y1, and x2, y2. So this will help us to find all the internal forces as functions of these coordinates. Then what do? Then it is the same. Make an imaginary cut through any of the sections, through any of the members. But here you need to cut only one member at a time. Why is that so? It is because you expose three unknowns with one cut. So, but you have only three equations of equilibrium. So you make only one cut at a time. Then you apply the equations of equilibrium. Now what will you apply? You need to apply all the three. So you need to apply sigma fx equal to 0, sigma fy equal to 0, and sigma m is equal to 0. Determine these and apply the suitable sign convention assumed while making a cut. So typically we take tensile axial forces. So if you have a member, we take tensile axial forces as positive. We take clockwise shears as positive, and we take sagging bending moments as positive. So this is the usual positive sign convention adopted for beams and frame members. Then let's get to the methods of. So we have looked at all the methods for determining the internal forces in statically determinate structures. The next step is to look at the various methods available for determining the unknown displacements in statically determinate structures. So the first one available for the analysis of statically determinate beams is the Macaulay's double integration method. So we know that. So the assumptions are the shear deformations and the axial deformations are very small. The axial strain and the shear strain in a beam is very small. Once you assume it, we can determine what is known as the elastic curve of the beam. So the elastic curve of the beam is nothing but the profile of the deflected beam under elastic bending deflections only. So when the beam is subjected to just bending deformation, the elastic curve of the beam is given by this equation, which is the m by ei, the moment at a section, divided by the elastic modulus and the moment of inertia of the cross section about the bending axis, is equal to d square v by dx square, where v is the deflected, v is the displacement, vertical displacement of a point in the beam, and it's an approximation to the curvature when the rotations in the beam dv by dx are much small compared to 1. It's very close to 0. Now establish the coordinate system for each segment. Now which segments are we talking about? So if there are discontinuities in loading along the beam, as shown here, if you have discontinuities in loading along the beam, so I need to consider this as one segment of the beam, this as the next segment of the beam, this as the other segment of the beam. So you consider one segment at a time, determine the bending moment in each of the segments as described in the previous method, and then integrate them twice with appropriate integration constants to get the function in to get the equation of the elastic curve in each segment of the beam. Once you have determined that, you need to enforce what is called as the boundary conditions and continuity conditions. Note that while determining the bending moment, we only take care of the reactions, but we don't enforce that the displacement at this point is actually zero. So since suppose you take this equation and when the bending moment is known, if you integrate it twice, you get two integration constants. Those two integration constants have to be determined for this beam by enforcing that the displacement at x equal to 0 for this beam is 0 and the displacement at x equal to L for this beam is L. And when we break the integration between multiple segments of the beam, you have to enforce that the slope and the deflection are continuous across the point where we break the beam into segments. So that is what is the boundary conditions and the continuity conditions. And as usual, the sign convention is upward deflections are positive and counterclockwise rotations are positive. So this sign convention goes well with the sign convention adopted for bending moments. Now, we'll solve some problem just to brush up your memory. So, but before that, let us also look at the other two methods available for determining the deflections in a statically determinate beam. So the next method we are going to look at is the moment area theorem. So there are two theorems. One is for determining the slope in a beam. So the first theorem states that the change in slope between two different points on the elastic curve. So as I said, elastic curve is nothing but the deflected profile of the beam. So the change in slope between 2 points on the elastic curve equals the area of the n by ei diagram. So it is nothing but the integration from a to b of m of x by ei, which is nothing but the area of the n by ei diagram between the 2 points. So that is quite straightforward. Where you need to make, so that gives the change in angle. It doesn't give the angle directly. You need to choose one of the points such that the change in angle directly relates to some angle or deflection or whatever. So that we need to take care. It only gives the change in angle. It doesn't give directly the angle or the displacement. Similarly, the vertical deviation of a point A on the elastic curve. So you have 2 points on the elastic curve. One is point A and the other is point B. The vertical deflection of this point with respect to a tangent drawn at another point is equal to the moment of the m by ei diagram between the 2 points. So the moment is nothing but integral x. So moment of any function is nothing but x f of x dx. So here our function is the m by ei diagram. So multiply that by x and integrate from a to b. But where should you measure this x from? That is an important thing. So here you need to measure x from the point where you need to find out the vertical deviation. Again, note that it is not giving the displacements directly. It gives something called the vertical deviation. So from this, if you choose the points A and B carefully, along with other relations, we can directly get the displacements. So we'll also be looking at this shortly. The other method is the classic conjugate beam method. So this beam, given a statically determinate beam, which let us call it the real beam, RB, first you find out all the reactions and the bending moment diagram. Once you have determined that, construct a conjugate beam with appropriate boundary conditions. So what are the appropriate boundary conditions? Those are given by the next two relations. We have the following two results, the proof of which has been already discussed in the lecture and also in my earlier tutorial sessions. So the slope in the real beam at a given point is equal to the shear force in the conjugate beam at the same point in the conjugate beam, at the corresponding point in the conjugate beam. So if you take at x is equal to a in the real beam, the slope at x equal to a in the real beam is equal to the shear force at x equal to a in the conjugate beam. Similarly, the displacement, the vertical deflection at x equal to a in the real beam is equal to the bending moment at x equal to a in the conjugate beam. But based on these two conditions, we need to transform the boundary conditions from the real beam to the conjugate beam. So we already saw that if we have a fixed support in the real beam, then it means that at that point we have no displacement and no rotations. So this corresponds to, so if we have a fixed support in the real beam, it corresponds to a free end in the conjugate beam. Why is that so? Because the displacement is equal to the moment in the conjugate beam. So this is the conjugate beam, and this is the real beam. So the displacement in the conjugate beam is equal to the moment. Displacement in the real beam is equal to the moment in the conjugate beam, and the shear force in the conjugate beam is equal to the slope in the real beam. Since both are zeros, this has to be a free end with no bending moment and no shear force. Similarly, if we have a hinged support in the real beam, it corresponds to a hinge support in the conjugate beam as well, because the shear force is zero in the in the real beam the displacement is zero, and in the conjugate beam the bending moment is zero. It also ensures that in the real beam the rotations are non-zero, and in the conjugate beam, just a minute. In the real beam, if the rotations are non-zero, it means that it is ensured by taking a hinge support at the conjugate beam, because the shear force is non-zero in a conjugate beam. And then if we have an intermediate support in a real beam like this, what does it mean? It means that the bending moment at that support is non-zero but continuous. The bending moment is non-zero and continuous. On the other hand, the shear force is discontinuous. So that corresponds to a intermediate hinge in the conjugate beam. So if you see, the displacements are, let me just see this. So if you have an intermediate support in the real beam, that corresponds to, so what are the conditions here? We have the vertical deflection is equal to 0, and the rotation is continuous. So rotation corresponds to the shear force. So shear force has to be continuous, and the bending moment in the conjugate beam has to be 0. So this corresponds to an internal hinge in the conjugate beam. And if you have an internal hinge in the real beam, what does it mean? It means the rotations are discontinuous and the displacement is continuous. So displacement is continuous means the moment has to be continuous and the shear force has to be discontinuous. And that is realized if you have an intermediate support in the conjugate beam. So these are the transformations of the boundary conditions from the real beam to the conjugate beam. Now let us take a simple example, right? So let us take a simple example to demonstrate all the three methods. So let us. This is the structure I'm looking at. So it's a overhanging beam. This is point A, point B, and this is point C. And this is subjected to a loading of 6 kilonewtons per meter in the span BC. As usual, the first step always is to determine, I didn't tell about these spans. So this is 8 meters. And this is also 8 meters. So the first step is to determine the support reactions. It is very simple. So take moments about the point A. How do you do it? So take moments about the point A. So you have RB into 8, which is a counterclockwise moment, minus 6 into 8 acting at 12 is equal to 0. So you get RB is equal to 6 12s are 72 kilonewtons. And what is RA? So the total downward forces 6 8s are 48 and this is 72. So this is upwards, and RA, so 48 minus 72 is minus 24 kilonewtons. So minus 24 means it is 24 kilonewtons downwards. So these are the support reactions. So as always with any method, the first step is to determine the bending moment diagram. So in span AB, you set up a coordinate system here. So let us call this x1 and let us call this x2. So in this span, the bending moment is linearly increasing because of the downward force of 24 kilonewtons. So the bending moment is negative here. So you have 24 acting at x distance. So as it comes to the point B, it is 24 times 8. So how much is it? So it is 24 8 are 192. So here you have minus 192 kilonewton meter. And on this side, at this end, the bending moment is 0 and it increases in a quadratic fashion due to a linearly distributed load. Here it is. Now what is asked? We are asked to find the deflection at point C. So it is negative. And we have the local coordinate axis. So it is quite simple. How do we do it? Let us first solve it by double integration. So another trick, instead of taking x2 from left to right, you can take x2 starting from the right side because it's not going to make any difference. You just have to enforce the continuity conditions correctly. So what is m of x1 in span 1? It is nothing but minus 24 into x. So integrate it twice, you get so you have d square d by dx square is equal to minus 24x by ei. So if you integrate it once, you get dv by dx is equal to minus 12x square plus c1, and you get v is equal to minus 4x cube plus c1x plus c2. So this is x1. This is in the first span AB. And in the span BC, what do we have? So this is span AB. And we have span BC. And in span BC, we have m of x2. It's nothing but minus wx square by 2, which is minus 3x square. So we get d square v by dx square is equal to minus 3x square by ei, which implies dv by dx is equal to minus x cube by ei. So that's an ei everywhere. Or rather, let me take the ei to the left hand side. So this is ei. So again, here also, let me take the ei to the left hand side. So this becomes minus x cube plus c1, which means minus ei v of x is nothing but minus x cube minus x power 4 by 4 plus c1x plus c2. Now we have four. So this c1 is in span 1 and this c1 is in span 2. So let me call it c3 and c4. So we have four integration constants, two boundary conditions. What are the two boundary conditions? The displacement at point A is 0, the displacement at point B is 0. And we have two continuity conditions, that is the displacement field is continuous at this point. So what are the, so let me enforce them. So boundary conditions are in span 1, right? In span 1, the boundary condition is v1 of x1 equal to 0 is equal to 0. So what is the function that we got in span 1? It is minus 4x1 square plus c1 x1 plus c2 is equal to 0. So we get c2 is equal to 0. And what is the other boundary condition? The other boundary condition is V2 of. In span 1, we have V1 of x1 equal to 8 meters is equal to 0. So what is that boundary condition? We get minus 4 into 8 cube plus C1 into 8 is equal to 0. We have already found that C2 equal to 0. So C1 is equal to 4 into 8 square. So that is 256. So we have determined this. And coming to span 2. In span 2, we have V2 of x equal to 8 is equal to 0. Note that the origin of the coordinate system in span 2 is in the right hand side, right? So it's on the right hand side. So you have to take at x equal to 8 meters. So which means, and what is the function there? We have minus x power 4 plus c3x plus c2. So minus 8 power 4 by 4 plus c3 into 8 plus c4 is equal to 0. What is the other condition? Now we have the continuity condition. So here we have continuity condition, continuity of slopes, because the continuity of displacements is already enforced by setting both of them equal to 0. The continuity of slopes is dv by dx in the first span at the point x equal to 8 is equal to dv by dv2 by dx, it is in the second span at x2 equal to 8. So enforcing this, what is it? What is the dv by dx in the first span? It is, we already have the expression here. So dv by dx is nothing but from this it is minus 12 into 8 square plus c1. And what is c1? It is 256. So minus 12 to 8 square plus 256 is equal to, what is dv by dx in the second span? It is minus x cube plus c1. So plus c3 minus x cube plus c3, and x is nothing but 8. So from this you can directly get c3 as 8 cube minus 12 into 8 square. So C3 is nothing but minus 256. Now substitute C3 into this. So we get C4 as minus so thus we have obtained. Now what is asked? We are asked to find the deflection at the point C. Right? So we are asked to find the deflection at the point C, but C corresponds to x2 is equal to 0. So let us determine that if you set x2 equal to 0 in the expression for this, so let us see. Yeah, there's a mistake here. So this is plus 256. So this turns out to be there's a calculation mistake here. Sorry for that. So this is actually minus 1024. So C3 is minus 1024. And then substitute this into this, we get C4 is equal to minus 8 power 4 divided by 4 minus 1024 multiplied by 1280. C3 is fine. Just a minute. So let me redo this part. So this part is fine. While enforcing the continuity of slopes, you need to take the derivative of the first one. So dv1 by dx is nothing but from this slide we have minus 4. You can take the factor ei out, minus 4 x1 cube plus c1 minus 12 x1 square plus c1. So here it is minus 12 x1 is 8 plus c1. And what is c1? C1 is 256 is equal to what is dv2 by dx? dv2 by dx is minus x cube plus c3. So this one is c3 since it is a second. So x2 is also 8. So we get 8 cube minus 8 cube plus c3, which implies c3 is equal to minus 12. So minus, so you can see this is nothing but minus 12 plus 8, and 256 is 8 square into 4. So this one is plus 4 into 8 square, which is nothing but 0. So C3 is equal to 0. Therefore, C4 turns out to be 1000. Let's see. So you determine C4, and once you determine C4, the deflection at the point C is nothing but C4 itself. So that is it. Then you can look at, let's go to the next method by using the moment area theorems. So this is the bending moment diagram. Let us call it as the M by EI diagram. We are required to find out the deflection at this point. Let us sketch the deformed profile, how it is going to look. So you are fixing this point. You are having an internal support at this point, and you're applying load here. So the deformed profile of the beam is going to look something like this. And we need to determine this, which is delta C. To get this, first let us find out what is the angle at this point, right? So if we find out what is the slope of this, so the idea is, let us draw a tangent here. What will this be equal to? This will be nothing but the tangential deviation of the point C with respect to a tangent drawn at the point A. And what is this? This is nothing but the tangential deviation of the vertical deviation of the point B with respect to a tangent drawn at A. But what is delta C? Delta C is nothing but so delta C is TC with respect to A minus TB with respect to A. So that is it. So since the displacements are downwards, let us take a modulus. So just to avoid the negative signs, we know this is going to be the deflected profile. So what is TC with respect to A? TB with respect to A is very simple. It is the moment of this triangle about the point B. So it is nothing but half into what is the area? So this maximum value we saw it is 192 by EI. So half into 8 into 192 by EI with a minus sign. And the centroid of the triangle is 1/3 of the length into 8 by 3. So how much is that? This turns out to be minus 2048 by EI. And what is TC with respect to A? So TC with respect to A, so you need to take the moment about this dot. So the centroid, you can add it up as, so area of AB, area of this triangle, which is minus half into 8 into 192 by EI into what is the lever arm? It is 8 plus 8 by 3. So it is 8 into 4 by 3 minus, you have this portion. So you have a parabolic spandrel. So if you remember, the parabolic spandrel has an area that is 1/4 of a, sorry, the parabolic spandrel is what you get by subtracting a parabola from a rectangle. So the area of a parabolic spandrel is 1/3 of a triangle. So if you have a rectangle and you're having a parabola, this area, so this is 3/4 of the area of the rectangle, and this is, sorry, this is 2/3 of the area of the rectangle, and this is 1/3 of the area of the rectangle. Or if you don't want to do it, you can directly integrate it as well. So we know that in this span, the moment function is given as minus 3x square, and you multiply that with x by EI to dx going from 0 to 8. So integration of 3x cube is nothing but 3 by 4 x power 4. So it is nothing but 3 by 4. So let us So the first one is minus 8192. This one is minus 8192 by EI. And this is nothing but 3 by 4 into 8 power 4. So 3 by 4 into 8 power. This is minus 3072 by EI. So the total values 11264. Now delta C can be directly determined as 11264 minus this thing. So you'll get a minus sign. That's why we are taking the modulus. So it is nothing but 9216 by EA. Just a minute. It's a factor of 2 that is missing, right? So here you have the so the vertical deviation of this point with respect to a tangent here is TBA, but this length is twice this. So this length is twice this length. So this will be nothing but 2 times TB with respect. So here this is nothing but minus 11264 minus 2 times of minus 2048 by EF. So this turns out to be 7168 by EF. So that is the answer. Delta C is equal to 7168 by EF. Now let us solve the same problem by the method of conjugate beam. So if you solve by conjugate beam method, what is the conjugate beam corresponding to this? So the real beam is something like this. So the free end will become a fixed end. The hinge support will remain hinge support. The intermediate support will become a internal hinge. And we have to load it by the M by A diagram, which means you need to load it like this. So the load is downwards if the moment is heavy. Maximum value as we saw is 192 by here. So as usual, the bending moment in the conjugate beam is equal to the displacement in the real beam. Therefore, delta C in the real beam is equal to the bending moment at the point C in the conjugate beam. So let us determine the support reactions in the conjugate beam. They're quite simple. Or yeah. So the total, if you take, so we know that the sum of all moments about the point B should be equal to so the support reactions can be determined as follows. So let us take moments about the point. So consider span AB and take moment about B. So which means we have RA minus RA into 8 plus we have a triangular load distribution, so we need to integrate it, plus 192 by EI, half into 192 by EI, acting through 8 meters at a distance of 8 by 3 is equal to 0, which implies RA is equal to 192 into 8 by 6. So RA is nothing but 256 by EI. Let us not determine, so it's in radians because it's the conjugate beam. And so if RA is so much, so what is MC? MC is nothing but minus RA into 16. Now consider the full beam at once. So if you draw the free body diagram of the full beam at once, it is something like this. You have RA here. You have an internal hinge. We really don't need to worry about it. And you have an unknown moment and a shear force here. So the loading is like this. So if you take moments about the point C, get MC minus RA into 16 plus the effect of the triangular loading. We already saw that this is the value plus half of 192 by EI into 8. It acts at 8 by 3 plus 8, which is 4 into 8 by 3. Plus, we also have the effect of the distributed loading, and that we have already determined it from the previous exercise as it is 3x square into x dx, which is minus 3072 by E. So putting them all together, we already have the expression for RA, which means MC is equal to 256 into 16 minus 192 into 4 into 8 into 8 by 6 minus 3072, which is minus 7168 by 8, which is precisely the same value as we got in the moment area theorems. So we have, and the minus sign denotes that the moment is hogging, which means the displacement in the real beam is downwards. So that is it. Now let's go to the next method, which is the principle of virtual work. So we have already seen what is the principle of virtual work. It states that at static equilibrium, if you have a body under static equilibrium, if you have a system of forces under static equilibrium, then the virtual work done by the forces on any kinematically admissible displacement is 0. So if you have a system of forces acting on a body to be in static equilibrium, then the virtual work done by the forces on any kinematically admissible displacement field is 0. So if you take a displacement field like this, which is kinematically admissible, that means it satisfies the support conditions. So any kinematically admissible virtual displacement field is 0. So that is all. Now, how is it useful in our case? We consider that suppose we have a body subjected to some forces, and we are expected to find the support, and we are expected to find the displacement of a given point. Say if this deforms this way, and we are interested in finding this displacement. Let us call it delta. So the idea is to first consider a virtual force acting at that body, acting at that point with a magnitude of 1. And then let us act upon it the real loadings. So if both these are statically admissible force fields, that is with appropriate support conditions, if you apply a unit force, the reactions will be generated such that this body is in equilibrium. Similarly, if you have the support reactions and you apply the applied loading, the reactions generated will be such that the body is in static equilibrium. So both of them have statically admissible force fields. And since the support conditions are satisfied, they will have statically admissible, kinematically admissible displacement field. Then the net work done by this force on the displacements here should be equal to 0. So the condition is 1 acting through the displacement. So the virtual force acting through the real displacements does no work because this is a kinematically admissible displacement field. That should be equal to the internal forces. The virtual internal forces, let us call them Fi. Right? If you take a small segment of the body, there will be a statically admissible internal force field, which is Fi, through the real displacement field, through the real internal deformation, let us call it dl, at every point in the body. So this is basically principle of virtual work for deformable works. You have a statically admissible force field and you have a kinematically admissible displacement field. Virtual work states that if the force field is statically admissible, for any kinematically admissible virtual displacement field, you will have 0 work. So this force will do work, 0 work on this displacement field, and this force will do 0 work on this displacement field. So the work done by the virtual external forces on the real external displacement should be equal to the work done by the virtual internal forces on the real internal displacements. So that is the total work done. Now, how do we apply it to the analysis of statically indeterminate structures? Sorry, analysis of statically indeterminate structures positive. So as I said, if we have a beam or a truss, and suppose you are expected to find the displacement of some point here, you place a virtual load at this point. And then, so remove all the real forces and determine all the real internal virtual forces. In the next step, you remove the virtual force and apply all the real forces. So they will deform in a certain manner. Then you apply the virtual work equations. So in one case, you remove the real forces, apply a virtual unit load. And then in the other case, you remove the virtual force and apply the real loads. Then the principle of virtual work states that the work done by all the internal forces. So the work done by all the internal forces, say in the case of a beam, that's an integral because a beam is continuous. So what is the internal force in a beam? We know that it's not shear deformable, it's not axially deformable, it is only bending. So the internal virtual moments acting through the real internal rotations. If you consider small segment dx of the beam, it rotates by d theta, which is given by the curvature times dx. And what is the curvature? It is nothing but the real internal force, real internal bending moment by EI. This we have already seen the double integration method. So in the ith member, if you see the bend, so since it is continuous, we have it as a function of x. This is the work done by the. So this is the work done by the virtual internal forces on the real internal displacements, real internal rotations, virtual internal moments on the real internal rotations. That should be equal to the work done by the virtual external force on the virtual real external displacement delta. So if this the real external displacement is delta, the work done by the virtual external force on the real external displacement should be equal to the work done by the virtual internal forces on the real internal displacements. So for a beam, this is the condition that we need to look at. And for a truss, since they are all discrete members, we know that there are, suppose the internal member forces are Ni and the internal displacements are Ni L by AE. So this is the condition. Summation over all members. If you apply a virtual external force at a given point that is equal to that acting on the real external displacement at a point in the truss is equal to the summation of all the virtual internal forces doing work on the real internal displacements. That's it. So these are the two forms of the unit load method applied to trusses and beams and also frames. Only in the case of frames, you need to split the integral into multiple parts for each beam member, frame member. So that completes all the methods available for analyzing statically determinate structures for both the internal forces and the deflections. Next, we get on to the analysis of statically indeterminate structures. So the first one among that is the theorem of three moments. So we have the Klepperon's theorem of three moments, which relates the. Suppose you have a continuous beam. It is not an internal hinge support, it is a continuous support. And if the points A, B, and C, and it is continuous on both sides, there may be as many spans as possible. We can have any number of spans, but this Klepperon's theorem of three moments relates only three moments at a time, which are continuous. So suppose this joint is subjected to a sagging moment of MA, and this joint is subjected to a sagging moment of MB, and this joint is subjected to a sagging moment MC. These three are related to each other by this grand equation, which is the Klepperon's theorem of three moments. Now, this is actually a statement of compatibility of the rotation. Compatibility equation, which is the continuity of rotation. Continuity of the rotation or the slope dv by dx at the joint B. So we have one equation, which is one compatibility equation at this joint. But we have three unknowns, which is MA, MB, and MC. So how do we solve for it? We need to consider three consecutive spans, one at a time, throughout the beam. So first we'll consider some span A, B, C. Next we'll consider this, this, and this. And we'll also have some certain support conditions. Using that, we can determine all the moments. So MA, MB, MC are the primary unknowns. MA, MB, MC are the unknowns. Rest are all geometric properties they are known. What is this? So AAB is nothing but the area of the bending moment diagram in the span AB, and XAB is the centroid of the bending moment diagram. So centroid of the bending moment diagram measured from point A. Similarly, ABC is the area of the bending moment diagram in the span BC, and XCB is the centroid of the bending moment diagram measured from C. So that is it. You know how it was derived, so I'm not getting into those details. And what are these two? These account for support settlement. So delta AB is nothing but the settlement of support A minus settlement of support B, and delta BC is nothing but the settlement of support B minus settlement of support C. This is not AB, this is BC. Make it clear, this is BC. BA. So that is it. But in case you have a fixed support, right? You have a fixed support, we cannot apply the Clapeyron's theorem of three moments because there's no support beyond that. In that case, what we do is we replace the fixed support by a rigid beam, a very short and rigid beam of length, of very short length, and it's a very rigid beam. And at the end, we can also enforce zero moment. That's not a problem. So here we have at this span, the moment ma is equal to 0, which is one equation. Here we have the Clapeyron's theorem of three moments, and here we have mc equal to 0. So we have three equations and three elements. So if you have a rigid support, you assume that extend the beam beyond the rigid support by a imaginary rigid beam. So that is it. It's a very simple method. You can do it. Now, if you wish, we can also solve some problems in the Clapeyron's theorem of three moments. So we have already solved many of them. Let us take this simple case. We have let us consider a prop cantilever of length 10 meters and an applied hogging moment of 20 kilonewtons. Suppose this is A and B. As I said, we have a fixed support here, so we cannot directly determine the moments here. So let us extend this beam by a rigid beam up to a point A prime, and let us support this point by a simple hinge support. So now this becomes an intermediate support, and here we have this. And note that this is rigid, this cannot deform. So for the rigid beam, EI is tending to infinity. Okay, so this span doesn't matter, whatever it is, because it's divided by length, and this is 10 meters. So what is the Clapeyron's theorem of three moments? MA, LA, which is L, divided by EI. So EI is very large, so this vanishes, plus 2MB, L by EI, LA, this is point A, and this is point B. So we have L by A prime A, but EI of A prime A is very large. So we have L A prime A by E A prime A, I A prime A. But this is very large. The denominator is very large, so it is 0. Plus L A B by E A B I A B. Plus, sorry, not NB, MA. Plus, this is A prime. Plus we have MB into LAB by EAB, IAB. This is equal to 0. But what is MB? Since it is a hinge support, MB is already 0. So we have only one unknown, which is MA. And what is on the right hand side? We have on the right hand side we have minus 6 A AAB XBA by LBA EBA IBA. So the other part does not contribute because LA prime A, E prime E, LA prime A is finite, but EA prime A and IA prime A are very large. So the other part will not contribute, which is nothing but, and you're subjecting it to a hogging moment. So the bending moment in the span AB will be like this. If, right? So what is the area under this? So AAB is nothing but half into 20 into 10, which is nothing but 100 kilonewton meter square. And what is X bar BA? X bar BA is nothing but 1/3 of 10. So that is it. So we have, and there is no support settlement. So on the right hand side, we have -6 into AAB is 100. X prime BA is 10 by 3 by LBA is 10. EI is just EI. On the left hand side, you have 2 times MA. What is LAB? LAB is 10 by EI. So 10 and 10 gets cancelled. Here you have another 10. So let us cancel this. And this becomes 2. And this 2 gets cancelled with this. So MA turns out to be minus 10 kilonewton. And there's a minus sign here. So this area is negative. So you have a plus. So that is the answer. So for this prop cantilever, by the Clapeyron's theorem of 3 moments, we have only one unknown. The other unknown vanishes because it's of a very stiff beam, and MB is 0 because of this. So this is how we. Then we are going to the method of consistent deformation. So let us try and solve the same problem by the method of consistent deformations. What is the procedure? To determine the degree of static indeterminacy. The first step is to determine the degree of static indeterminacy. And then we need to identify the redundant forces. So once you have determined the degree of static indeterminacy N, find out N redundant forces, remove them to construct a statically determinate and stable primary structures. So we decompose this given system into a sequence of primary structures. So suppose we have, as in the previous case, suppose we had a prop cantilever like this, subjected to a moment. We decompose into 2 parts, one subjected to the moment alone and one subjected to this. So the net result is the, and when we do this, we find the unknown force such that the compatibility condition is satisfied. So we decompose the given system into a sequence of primary structures that are statically determinate and stable. One subjected to the applied load, one subjected to the first redundant reaction, then second redundant reaction until all the end redundant reactions are done. Then we use the principle of superposition and enforce the compatibility of displacements. So what is the compatibility condition in this problem that we consider? Here it is that the deflection of the end should be equal to 0. That is the compatibility conditions. Then we also have what are called the flexibility coefficients and the load induced displacements. So let us solve the same problem by the same problem as that of the Clapeyron's theorem of 3 moments by this method. So we had something like this. So the degree of static indeterminacy for this problem is 1. Why? We have 4 support reactions and 3 equations of equilibrium. Now, what do we treat as the unknown? Let us treat the moment at this support as the unknown force. So if I release that, I get a simply supported beam. And here we have a primary moment, which is -20 kilonewton meter. So this I am decomposing it into two parts. One is this primary structure subjected to the applied loading plus the primary structure subjected to the redundant loading. Let us call it X1. Now we define something called, so what is the condition, compatibility condition? So let us suppose this makes the beam deform like this, causing something, causing a rotation of dl due to a d at the degree of freedom 1. So this point d1l due to the applied loading plus here what is it? Here you have a displacement at the point 1 due to the redundant force applied at the point 1. So here it is nothing but F11 x1. F11 is the displacement at this point due to unit force applied at this point, which is F11 multiplied by x1 because the magnitude is x. So how do we determine F11? F11 is nothing but you apply a unit. F11 is nothing but m1 by ei dx. So the compatibility condition is F11 x1 plus d1l is equal to 0. So M1 is the moment generated in the beam due to an applied unit virtual force. So what is this? So for this beam, the bending moment diagram is something like this. So I'm applying X1, so it's like this. One. So this area is nothing but 1 square by EI. So it is simply 10 meters. It is just 10 by EI. So it is half into so here it is 1 minus x by 10, the whole square divided by EI into dx, going from 0 to, or rather, take the coordinate system from this side, x, so 0 to integral 0 to 10, x squared by EI dx, which is nothing but x cubed by 3, which is 1000 by 3EI. And what is d1L? d1L, using the principle of virtual work, we can have it is the work done by the virtual internal forces Mi on the real internal displacements Mi by EI dx from 0 to 10. So here it is nothing but x. The virtual internal moment is x. The real internal moment is minus 20 plus x, minus 20 plus 2x. Note that when x equal to 10, this becomes 0 by dx, 0 to 10. So what do we get? This turns out to be minus 20x squared by 2, which is minus 10x squared, which is minus 1000, plus 2x squared. If we integrate, we get 2x cubed by 3 plus 2 into 10 cubed by 3. So this is So this is minus 20 into x squared by 2. So there's an x by 10 here. Sorry, wait. Here it is. So letting f11 x1 plus d1l equal to 0 is also 10 x1 by 3i minus 100 x1 by 3i is equal to 0. So we get x1 is equal to 10 kilometers per hour. So that is precisely what we got by the previous method as well. By the method of Clapeyron's three moment theorem. So that satisfies. So this is how we use the method of consistent definitions. Then here we come to the last method, which is the slope deflection equations. So this is a displacement method. So the primary unknowns are the thetas and the sways. So the rotation at every joint is the primary unknown in this case. So the first step is to determine the degree of kinematic indeterminacy. So after ensuring compatibility, then you take one span at a time, obtain the fixed end moments due to the applied loading. So actually the joints are not fixed, they will rotate, but we can consider it as a superposition. The moments that are generated at the joints as a superposition of what will be generated if they're not allowed to rotate only due to the applied loading, plus what will be generated due to the applied load, due to the rotation without the applied load. So in the reality, there is a rotation and applied loading. So this part comes from. So we have this. This part comes from the rotations, joint rotations without any applied loading, and this comes from the applied loading without any joint rotations. And this one comes if there is a chord rotation in the wing. So if some support is settling by delta or the frame is swaying by some delta, then without any joint rotations, then this is what is generated. So we consider the expression for the bending moment generated at a joint due to the action of the due to the action of the loading alone, due to the action of the rotations alone, and due to the action of the sway alone. We add all of them, you get the total moment, which is an unknown yet because theta A, theta B, delta. Similarly, to the other end of the span also, we apply this. Then what do? Once you have identified the degrees of freedom, theta A, theta B, delta, and so on, we need to write an equilibrium equation for every unknown degree of freedom. So corresponding to every rotation, we have what is called as the joint moment. So the moments have to be 0 wherever we have assumed a rotation degree of freedom. Similarly, wherever we have assumed a delta, which is a sway degree of freedom, we need to enforce that the shear forces are in equilibrium with the applied forces. So that is the key idea. Once we have done this, we have set up the system of equations. Then you solve the system of equations for all the unknowns theta A, theta B, and delta. So let me take a simple problem as usual. So let us take this problem. So are there any doubts at this stage? I didn't get any doubts. Yeah, I understand it's all already covered, but the purpose of this session is only to have a quick revision of all the concepts. So you can also post it in the uh, discussion forum or the comments. I'll clarify it later on. Let us consider this problem. Okay. So we have a yeah, we have a portal frame. Here you have a load of 40 kilonewtons. Span of the frame is 15 meters. And this is 18 meters. And this one is 12 meters. So let us find first step as usual is to determine the degree of kinematic indeterminacy. So what are the kinematic unknowns in this? To determine that, let us plot the approximate deformed shape. We'll deform something like this. So there's a rotation here and there's a sway here. So let us call this theta1 or let's name it ABCD. So we have theta B, theta C, and you have a sway which is delta. And if this members are assumed to be actually rigid, you don't need to consider delta 1 and delta 2. Delta here will be the same as the delta here. Delta is the same as that delta. Now it's very simple. So the kinematic unknowns are theta B, theta C, and delta. So the degree of kinematic indeterminacy is 3. Next step, write down the slope deflection equations. So what is MAB? So we don't really need MAB. We can start with fine. MAB is 2 theta B, 2 EI by L theta B. So 2 EI by 12 theta B minus 6 EI by 12 square delta. And MBA is equal to 4 theta B, 4 EI by 12 theta B minus 6 EI by 12 square theta. Similarly, we have MBC is 4 EI by L theta B plus 2 EI by L theta C. Is there a sway? Is there a degree of freedom, sway degree of freedom? No, you should be careful because the sway is horizontal and this member is also horizontal. So that is not causing any relative rotation of the member. So there is nothing that gets added here. Similarly, MCB is 2 EI by L theta B plus 4 EI by L theta C. And what is MCD? And L is what? L is 15. MCD is equal to 4 EI by L theta C minus 6 EI by, here L is 18, 6 EI by L square delta. And MDC is equal to 2 EI by L theta C minus 6 EI by 18 square delta. So therefore, the next step as usual is to enforce equations of equilibrium at the joints. So sigma MB is equal to 0, which is nothing but MBA plus MBC is equal to 0. So what is MBA? MBA is this 4A by 12 theta B. Let us find out the numerical values. So 4 by 12 is 1 by 3. So this is nothing but theta b by 3 minus 6 by 12 square. 1 by 24. Delta. And what is this equal to? MBC is 4 by 15 theta b plus 2 EI by 15 theta c. This is 2 EI by 15 theta b plus 4 EI by 15 theta c. And this turns out to be 4 EI by 18 is 2 by 9. 2 EI by 9 theta c minus 6 by 18 square. So that is 1 by 54. Similarly, this turns out to be 1 EI by 9 theta c minus 1 EI by 54 delta. So MBA plus MBC will be, so theta B coefficient is 1 plus 4 by 50, which is 19 by 50. So we get 19 by 15 EI theta B. And what is it for delta? It is minus 1 by 24 minus delta EI by 24 is equal to 0. And sigma MC equal to 0 implies MCB plus MCD is equal to 0. So what does that result in? MCD is 2 theta C coefficient is 4 by 15 plus 2 by 4 by 15. 22 by 45. So we get 22 EI by 45 theta C. Plus what is the coefficient of theta B? Theta B is 2 by 15. Minus EI by 54. Is equal to 0. Note that we have got two equations of equilibrium. As I said, the last one should be coming from the column shears. So consider column AB. So column AB, the shear force is so if you consider column AB, the forces are like this. The moments are all clockwise, and the shear force, if you take in this direction, the shear force is minus MAB plus MBC by LA, MBA by LAB. What is this equal to? MAB is 1 by 6 plus 1 by 3, which is EI theta B by 2 plus what is the by 12. This is the shear force in the member AB. Similarly, if you consider the column CD, it is minus sign here. So you have minus MCD plus MDC by LCD is equal to, if you add the two, we get 2 by 9 plus 1 by 9, which is 1 by 3. 1 by 3 theta C. minus AI by 50. By LCD is 18. So this turns out to be theta b times EI by 24 minus plus EI delta by 44. Here it is minus EI theta c by 54 plus EI delta by 486. Now, what is the equation of what is the we want the summation of horizontal forces to be equal to the applied force. So the applied force is 40 kilonewton. Where is it? So 40 kilonewtons rightwards, and the reactions are VAB and VCD. So VAB plus VCD should be equal to 40 kilonewtons. Now, how do we find that? So VAB is this. So minus EI by 24 theta B plus minus EI by 54 theta C summation of these two. So 44 EI delta is equal to 40 kilonewtons. So we have got the third equation as well. So this is equation 3. This is equation 1. And this is equation 2. So this system of equation can be easily solved in the form, so you get a coefficient matrix multiplied by theta b, theta c, delta is equal to 0, 0, 40. So you can fill in the coefficients. If you solve for this, you can do it right now. The 3 by 3 system. Since the degree of kinematic indeterminacy is 3, we get a 3 by 3 system. So first coefficient is 19 by 15. Second coefficient is 2 by 50 minus 1 by 24. 0. 2 by 15. 2 by 45. Minus 1 by 53. 0. The last equation is minus 1 by 24. Minus 1 by 54. And 9.002. So we get theta b is equal to 165.1 by ER. Theta c is equal to 165.1 by ER. Delta is equal to 5547.25. So that is it. So the idea is to demonstrate how do you solve these problems with a side sway when you have using the slope diffraction equations. Now, this I don't think it requires explanation because we just did it 2 weeks ago. As we already saw, the moment distribution method gives an iterative solution. We don't need to solve systems of linear equations as we have been doing with all the other methods. First step is to identify the joints, compute the stiffnesses and distribution factors. So we remember that the stiffness, so the joint stiffness we saw. If we had, if the far end is fixed, we saw that the stiffness is nothing but 4 EI by L. And if the far end is hinged, the stiffness is something like 3 EI by L. And if the far end has a guided roller, the stiffness is, I think, EI by L. You can verify whatever it is. And the total joint stiffness is nothing but the stiffness of all the members connected at a joint. Like, you have a system like this. The total joint stiffness is nothing but when applied a compatible rotation, all of the beams rotate by theta. So the total joint is nothing but K1 plus K2 plus K3 and so on. So we had something called the distribution factor, which is the ratio in which an applied moment gets transmitted to the members connected at the joint. So distribution factor, we defined it as for the ith member, it is Ki by sigma K. Very simple. So this doesn't have any big establishing of equilibrium. So it is just algebra. So once we get the stiffnesses and the distribution factors, the next step is to compute the fixed end moments. What do? We are assuming that it is very similar to the slope diffraction method. We are constructing it as a superposition, but here we are not solving it directly. We are distributing the moment such that equilibrium is attained. So we assume all joints are locked from rotating. So whatever load we apply will transmit the fixed end moments. But those fixed end moments will not be in equilibrium because the joints are not actually fixed. So there will be a moment imbalance. You find out how much is the moment imbalance by summing up the total positive and negative moments at a joint. And whatever value we get, apply negative of that moment to the joint so as to equilibrate the imbalance. Now, when we release the joint and apply the moment, we know that this joint is undergoing a same rotation, one rotation, and all the members connected to the joint are also undergoing the same rotation. So the moment the applied moment gets distributed according to the distribution factors. Once you do that, so apply a moment M. So we have the table distribution factors 0.6 and 0.4 for the span AB. At the point B, you allot 0.6 M and you allot 0.4 M. And you see, and you carry this over to the fixed end support. So if you have a beam like this, with some applied loading, initially whatever fixed end moments we get will not be in equilibrium. There will be a moment imbalance M. Distribute that moment imbalance according to the distribution factors. And by distributing, it means we're applying so much moment and allowing the beam to rotate. But if the beam rotates, it transmits half of the moment to the fixed end. So here you'll get some 0.3 M and 0.2 M. And from somewhere else, you can get some moment here. Then look at the moment imbalance at each joint. If it is all balanced, then no need to do anything further on. If it is not balanced, repeat the cycle until the moment imbalance reduces to a very small value. Also note that if you have a fixed support, if you have an actually fixed support, you don't need to worry about the moment imbalance because it will be absorbed. The fixed support can take infinite any moment without rotating. So that's not an issue. So keep repeating steps 3 and 4 until the moment imbalance reduces to a very small fraction and sum all the distributed moments. So that will complete the procedure. In case the frame that we are looking at has a side sway, you consider only the applied moments, applied loads at once. Then you consider an arbitrary shear force and solve the entire problem again for the side sway. So it's a slightly lengthy process. You can look at the week 10 video. The last problem in week 10 I have solved by that method. It is slightly lengthy, but it can be done. So you need to carry. So if there are two sway degrees of freedom, you need to carry out two moment distributions, one for the applied forces and the other for an unknown sway degree of freedom. Assume the unknown sway is some quantity, some delta. Take it to be any arbitrary value and solve the and carry out a moment distribution. Find out the moments, shear forces, and then you enforce the equilibrium of shear forces. So that is the final step. So you need to superpose these two. So if you have something like this with a load that is asymmetrically applied, you superpose it as make it a non-sway frame. So a non-sway frame has a support reaction x1. Apply negative of the support reaction here. So therefore something like this. Apply negative of the support reaction without any loading. So this you will get a moment distribution table. For this you get a moment distribution table. So here you will get a set of moments. Here you will get a set of moments. Now how do you combine these two? So find out how much is the reaction force, apply that, and then for that factor you add them up. That will be your net moment M total. So not just the moments, you can also get the shear forces, the displacements, rotations, everything can be added up in this question. So that is the crux of the method. All of you will be familiar with it since it was done recently. Let me go to the direct stiffness method, which we just did last week. So I don't think it requires much of a revision. So direct stiffness method, as we have already seen, it consists of many parts. The first part is to set up the problem itself. If you have a truss or a beam or whatever, always reduce it to an assembly of members and nodes. So wherever you have a joint or a concentrated loading, you treat them as nodes. If you have a concentrated loading, treat them as nodes. And where you have and the regions in between the concentrated loading subjected to continuous distributed loading, you can treat them as members. So divide the structure into elements between concentrated loadings or other discontinuities and nodes. So identify each member. So if you take member 1, it is between nodes 1 and 2. If you take member 2, it is between nodes 2 and 3. If you take member 4, it is between nodes 2 and 4. So identify this, establish the global coordinate system. So establish a global coordinate system and mark the degrees of freedom at each node. You can call it U1, U2, U3, U4, and so on. Mark the global degrees of freedom. Once you have done that, establish the unknown displacements. So wherever you have a reaction, everything is unknown. And the good thing is you don't need to solve for the reaction, even if the structure is statically determinate. It will follow naturally when we solve for the displacement. So no need to find out the reactions. Keep them as unknowns. And whatever is known, right? Wherever we have a known applied force, if you have a known applied force, make them into a matrix. So corresponding to every degree of freedom, there is a force. If it is known, assemble them in a matrix, a column matrix. Then compute the element stiffness matrix using this formula. So we have already seen this. This is the frame element stiffness matrix. If you wanted to get it for a beam element, strike out the first row, fourth row, first column, and fourth column. Whatever remains that is for a beam element. If you wanted to get it for a truss element or a bar element, strike out the rows 2, 3, 5, 6, and columns 2, 3, 5, 6. You get a 2 cross 2 matrix for a bar element. So this is in the local coordinates. So this is something like this. So if you have a member like this, So this is U2, V2, theta 2, U1, sorry, theta 1, U1, V1. And the corresponding forces are F1, F1y, M1, M1. So this is in the local coordinates. But if the beam is oriented, if the frame is oriented somewhere like this, the global coordinates are like this. So to transform it from the local to global, you need a transformation matrix, which is given by this. So the global stiffness matrix is related to the local stiffness matrix in this form. K global is equal to T transpose, K element, T, where T is this. And then you mark for each element stiffness matrix, what is the node it actually corresponds to? What is the global degree of freedom it corresponds to? So if you have a frame like this, subjected to some loading, you can, if you write down the element stiffness matrix for this this member, it is actually, and if you have the degrees of freedom as 1, 2, 3, 4, 4, 5, 6, and 7, 7, 8, 9. So this actually corresponds to degrees of freedom 4, 5, 6, 7, 8, 9. Relates the forces at 4, 5, 6, 7, 8, and 9. So this is the, and then assemble the structural stiffness matrix, right? If you see a member, if you see an element of the element stiffness matrix corresponding to 4 and 4, take the structural stiffness matrix and add it to the stiffness term 4 and 4. So that is how you do it. Then partition the matrix into known parts. So these are the known parts and these are the unknown parts. So wherever you know that forces, there the displacement is unknown. Where you know the displacement, if say if you set displacement is equal to 0 at some point, it means it's a support. So the forces are unknown. So first consider this system. You consider the top system that can be solved directly because this is unknown, this is known. K12s are multiplied with known displacement, so they can be solved. Once you get this, you can get all the support reactions by substituting into this. So once you solve for the du, substitute into this and get the known forces, unknown forces. So that is the direct stiffness matrix, a direct stiffness method. And in the presence of distributed loading, we also saw in the last session that if you have something like this, something like this, for this member, you take it as a superposition of this plus this. So if these two are fixed, there will be certain fixed end moments that are generated. Apply negative of the fixed end moment and add it to that. So that will correspond to the usual beam, beam with the distributed load. So which means that if you have a distributed loading like this, you can always replace it with the negative of the fixed end moments acting on the beam. This will not enter the stiffness matrix because for fixed ends, the slopes and displacements both are zeros. So this will not enter the stiffness matrix. So this is taken care by just altering the load force vector, right? The force vector, you just alter it by applying the negative of the fixed end moments that is in. So that brings us to the end of this session and also to the end of this course. So hope this session was very helpful for you. You can ask any doubt if you have. Is there any doubt? Okay, so the recording will be uploaded to YouTube and the slides will also be uploaded to the folder, drive folder. I hope it's useful for you for your exam next week. So wish you all the best and please provide your feedback in the form. I had a good time teaching the problems. So in case you have any feedback, suppose something can be improved, please provide that. And wish you all the best for your exams. Thank you. Let me end the session right here. If you have any doubts, feel free to post it in the forum or in the YouTube comments. Thank you all. I'm ending the meeting right here.